So today we are going to learn lesson 8. From today, the second half of unit 1 is about some concepts regarding the rational functions. And we'll be studying some particular some graphs of particular rational functions. So today's learning goals, first is to understand the definition of rational functions, and then we will be able to sketch or recognize the graph of functions of the form fx equals a over kx minus m plus c and analyze their properties. And then we'll also be learning to sketch or recognize the graph of functions of the form fx equals a ratio between two linear functions and analyze their properties. So this lesson will be broken into the four parts here. First of all, we'll have a look at the definition of rational functions, and then let's do a brief review of the function fx equals the reciprocal of x, and then the transformations of the function of fx equals 1 over x, and then we'll have a look at the fraction between two linear functions. All right, first of all, the definition of rational functions. I'll read the concept here for you. A function fx is called a rational function if and only if it can be written in the form fx equals px over qx, where px and qx are both polynomial functions of fx. And of course, qx is not zero function because zero cannot be a denominator in the real number set, right? For example, the following functions are all rational functions. 1 over x, 2x plus 3 divided by 6x plus 5. And some reciprocal, the reciprocal of some quadratic function. And x squared plus 2 over x squared plus 1, etc. And these functions here are not rational functions. So first of all, sine x, this is trigonometric function, right? 2 to the power of x, this is called exponential function. It's not a rational function. Log 3x, this is called logarithmic function. Also, it's not a rational function. Fx equals square root of x. Again, according to the definition, this is not a rational function. Okay, so before we proceed, let's do a brief review of the function fx equals 1 over x. We have studied the graph of this function in lesson 1, right? So do you still remember that the graph of this function looks like this, right? So first of all, the domain is any real number that is not 0, right? X cannot be 0 because it's a denominator here. Or if you use interval notation, it's negative infinity to 0, union with 0 to positive infinity, right? Okay, the range is also negative infinity to 0 and 0 to positive infinity. This graph passes point 1, 1 and minus 1 and minus 1. These are the two typical points, right? And this function is an odd function, having point symmetry about the origin point. And we can also see that when x is greater than 0, this function is monotonically decreasing with an increasing slope. The slope, although this function is monotonically decreasing, the slope is increasing, right? And when x is less than 0, the function is monotonically decreasing, but with an but this time with a decreasing slope, right? Okay, and behavior. When x approaches positive infinity, y approaches 0 from the positive side. When x approaches negative infinity, y approaches 0 from the negative side, right? And the horizontal asymptote is y equals 0. That means the x-axis is its horizontal asymptote, right? And when x approaches 0 from the negative side, from the positive side, y approaches positive infinity. And when x approaches 0 from the negative side, y approaches negative infinity, and the vertical asymptote is x equals 0, which is the y-axis, right? I hope you can understand the graph here and do understand the main properties of the function fx equals 1 over x, because our next discussion will be based on the graph and properties of the function 1 over x. Okay, next, let's try to consider the transformations of the function fx equals 1 over x. So consider another function with the form here. Gx equals a over kx minus m plus c. A, k, m, c are all constants, where a is not 0 and k is not 0, right? So by first glance, probably this function can be transformed from the function fx equals 1 over x, right? So let's have a look at how we can do this. So this time, let fx be 1 over x. Note that gx can be rewritten in this way, right? We can put the k in front, and what's left behind is x minus k over m, right? And then plus c. And then, as you can see here, if you rewrite gx with this form, gx is actually a times f k times difference between x and k over m, and then plus c, right? So if you rewrite gx using this form, this is actually a transformation from fx, right? Four parameters are a, k, k over m, and c, right? A corresponds to a vertical stretch or compression. And if a is less than 0, a reflection in the x-axis. And k here corresponds to a horizontal stretch or compression. And if k is less than 0, also a reflection in the y-axis, right? And c here is the easiest one. This is just a vertical translation up or down by v unit, right? And k over m here corresponds to a horizontal translation to the left or right. Okay, so I hope you can have a general concept of the translation of the function fx equals 1 over x. So now let's have a look at an example to illustrate this concept. So now consider the function fx equals 1 over 2x minus 1. So there are three questions. First of all, describe the transformations that must be applied to the graph of this function, gx equals 1 over x, to obtain the graph of fx. That means how we can get from gx to fx, right? Next, sketch gx and fx in the same 2D Cartesian plane. Question C, state the domain, range, asymptote, and end behavior of fx. Okay, so in order to transform gx to fx, we need to decide what are the 4 parameters, right? So note that fx equals 1 over 2x minus 1. We can rewrite this function. So following the concept here, we can rewrite this function in this way, right? We can put 2 in front and then x minus 1 over 2, right? And then as you can see here, the expression here is actually g x minus 1 half and then time a 2 in front, right? Can you see that? So now the transformation is actually from gx to g twice of the difference between x and 1 over 2, right? So this is the parameter k, and this is our parameter k over m, right? Okay, so what are the translations? So first of all, if you have a parameter here, we all do this first, right? So first of all, we need to horizontally compress, right? Compress gx by a factor of 1 over 2, right? And then second translation is to translate gx left or right, right? Because you have a minus 1 over 2 here, we need to translate horizontally to the right by 1 over 2 unit, right? Okay, so if you draw the function, if you sketch both of the functions in the 2D Cartesian plane, this is the original function, right? And in order to get the transformed function, first of all, compress horizontally and then translate horizontally to the right by 1 over 2 unit. So the vertical asymptote will come here, right? X equals 1 over 2. So this is the new function. New function will look like this. Right, and there is a y-intercept. Let's calculate the y-intercept then. Y-intercept is 1, when x is 0. When x is 0, the fx is minus 1, right? So minus 1 here. All right, next, the domain. The domain is x can be any real number that except the number that makes minus 2x minus 1 being 0, right? So 2x minus 1 cannot be 0. So that means the domain is x belongs to the real number set, but x cannot be 1 over 2, right? Okay, the range. The range is the same with the function here. It is negative infinity to 0 union with 0 to positive infinity. That means it can be any real number except a 0, right? Asymptotes. The horizontal asymptote is y equals 0. Vertical asymptote is x equals 1 over 2, right? Okay, and behavior is when x approaches positive infinity, fx approaches 0 from the positive side, right? And when x approaches negative infinity, fx approaches 0 from the negative side, right? And when x approaches 1 over 2 from the positive side, fx apparently approaches positive infinity, right? And then when x approaches 1 over 2 from the negative side, fx approaches negative infinity. Understand? All right, so now let's have a look at a practice. So this time I'll leave you 3 minutes to figure out this question by yourself. All right. All right, have you finished? Okay, so first of all, let's have a look at the possible transformations we can do to get this new graph from gx equals 1 over x. So note that fx can be rewritten as minus 3 over, you can put 2 in front, right? and 2 times x minus 5 over 2. And now actually you can see that this is actually g, first of all, x minus 5 over 2, right? And then put a stretching factor 2 here, and then the whole function of gx multiplied by 3, right? And this is a stretching factor here, a stretching factor here, and a horizontal translation factor here, right? And then you can see that actually our task is to transform gx to minus 3g to x minus 5 over 2, right? Okay, so first step is to do this transformation, right? You can stretch vertically by a factor of 3, right? And then because there is a negative sign, so we also need to reflect in x-axis, right? And the next we'll do the stretching here. Then because 2 is greater than 1, so this time we need to compress, right? Compress horizontally by a factor of 1 over 2, right? Okay, next is to do the transformation corresponds to the factor here. So next we need to translate horizontally to the right, because you have a negative 5 over 2, right? To the right by 5 over 2 units, right? Okay, so basically we can sketch the graph of fx now. Originally, gx has a vertical asymptote in the y-axis, right? So everything now is moved to the right by 5 over 2 units. So the new asymptote must be here, right? And remember that we also did a reflection in the x-axis. So this new function will look like this, right? Probably there is a y-intercept. So let's calculate the y-intercept. So let x be 0. When x is 0, fx equals minus 3 over minus 5, which is 3 over 5, right? So this point here must be 3 over 5. And this point here is 5 over 2. Okay, so this is a sketch of the new function. And as you can see here, there is no x-intercepts, right? Okay, so vertical asymptote, x equals 5 over 2. Horizontal asymptote, simply y equals 0, right? Domain, again, the domain is x can be any real number, but x cannot be the number that makes the denominator be 0, which is minus 5 over 2, right? And range. Range is any real number except 0. Or you can also write in the interval notation. Either one will do, okay? And behavior. When x approaches positive infinity, y approaches 0 from the negative side, right? will go in this way. And when x approaches negative infinity, y approaches 0 from the positive side. And when x approaches 5/2 from the positive side, y approaches negative infinity, right? And when x approaches 5/2 from the negative side, y approaches positive infinity. This is the end behavior. Okay, question D. State the interval where fx is increasing and the interval where it is decreasing. There is no decreasing interval, right? The increasing intervals are 2. There are 2 increasing intervals. So 2 increasing intervals. They are, first of all, from negative infinity to 5/2, exclusive. Next increasing interval is from 5/2 to positive infinity, right? Okay, do you have any questions? All right, you can also check the solutions here after the class, okay? I'm not gonna write all the details for you. Please do have a look at this question by yourself after the class. Okay, next one, let's have a look at another practice. Determine possible equation to represent the function shown below. Okay, I'll give you 2 minutes. Okay, any thoughts? Okay, so note that this function have a pattern that is similar to y equals 1/x, right? And the only difference is it seems that this function moves translate left from this function, right? Okay, so this is -3 here. So first of all, this function can be expressed as x plus 3, right? Because we have moved the x equals 1/3 to the left by 3 units. And probably it will also have a stretching factor. So let's put a k here. So in order to find value of k, we need to find a point on the function, right? So this this function passes through this point, which is -2, 1, right? So let's put this point in to check the value of k. That means 1 equals 1 over k times 1, right? So k is apparently 1. So the expression of this function is 1 over x plus 3. This is our final solution, right? Okay, any questions? No? All right, let's have a look at the fraction between two linear functions. So this time we have a function with the form ax plus b over cx plus d, where c is not 0 and ad is not equal to bc. This is actually this function here can also be translated from fx equals 1 over x. These two functions are also connected, right? Because gx can be rewritten in this way. If we put cx plus d unchanged, and then put a cx plus d in the numerator, in order to get ax plus b, we need to compensate it with a b minus ad over c here, right? So according to this way, the gx can be rewritten in the form here. Understand? And here you can see this is a vertical stretch factor, right? And the factor here is a horizontal stretch or compress factor. And the factor here is the horizontal translation factor. And factor here is vertical translation factor, right? So that means gx can also be translated from fx, right? Do you understand? Okay, so this is the concept behind the translation from fx to gx. Now let's have a look at a concrete example to illustrate the concept we have learned in the previous slide. So now let's consider the function fx equals x minus 5 over 2x plus 5. This is a ratio between two linear functions, right? First of all, describe the transformations that must be applied to the graph of the function gx equals 1 over x to obtain the graph of fx, and sketch the graph of fx. Then state the domain range, x and y intercepts, asymptotes, if any, and then end behavior of fx. Okay, so according to the discussion above, we can rewrite fx in this way, right? So first of all, keep the denominator unchanged and try to come up with the denominator in the numerator. So if we put a 2x plus 5 here, in order to get the x minus 5, we need to compensate with a factor of 1 over 2 first, and then if you put a 1 over 2, you can have an additional 5 over 2, right? So you need to subtract the 5 over 2 and then put the minus 5 in the original expression. So in this way, the fx is rewritten in this way, right? And this is actually, as you can see, we can put the minus 15 over 2 in front, and denominator can be rewritten as 2 times x plus 5 over 2, and then plus 1 over 2, right? And this is actually some translation applied to gx, right? This is a vertical stretch or compression factor. This is a horizontal stretch or compression factor. And then this is a horizontal translation factor. And this is the vertical translation factor, right? So from gx to fx, we need to do the following transformations. First, we need to vertically stretch the gx by a factor of 15/2, which is this factor here, right? Because you have a minus sign here, then we need to reflect gx in the x-axis, right? Okay, next step, horizontally compress gx by a factor of 1/2, which corresponds to the factor here, right? Then horizontally translate gx to the left by 5/2 units, which corresponds to the factor here. Last, vertically translate gx by 1/2 unit up. Right, which corresponds to the factor here. Okay, so the end behavior. When x approaches positive infinity, y should approach 0 from the positive side, right? And when x approaches negative infinity, oh, sorry, there is a typo here. When x approaches positive infinity, y approaches 1/2, right? And when x approaches negative infinity, y approaches 1/2 from the negative side, from the positive side, right? And when x approaches (5/2) from the positive side, y should approaches negative infinity. And when x approaches 5/2 from the negative side, y approaches positive infinity, right? Sorry about the typo here. Please make the correction by yourself. All right, let's look at the domain. Domain is x belongs to the real number set, but x cannot be -5/2, which will make the denominator be 0, right? Range is any number except 1/2. Vertical asymptote is x equals -5/2. Horizontal asymptote is y equals 1/2. And x-intercept is 5, 0. Y-intercept is 0, -1. You can simply put x being 0 into the original function to get the y-intercept, and put y equals 0 to the original function to get x-intercept, right? Okay, any questions? No? All right. So now let's have a look at the key features of the function fx equals ax plus b over cx plus d. So the equation of the vertical asymptote can be found by setting the denominator equal to 0 and solving for x, provided the numerator does not have the same 0, right? And then the equation of the horizontal asymptote can be found by dividing each term in both the numerator and the denominator by x and investigating the behavior of the function as x approaches positive or negative infinity, right? And then the coefficient bx to stretch the curve, but has no effect on the asymptote domain or range. The coefficient d shifts the vertical asymptote. The two branches of the graph of the function are equidistant from the point of the intersection of the vertical and horizontal asymptote. Okay, so we can now make a conclusion. Based on the discussion above, we have another way to quickly sketch the graph of function gx equals ax plus b over cx plus d, right? So let's have a look at the quicker way to sketch the graph of the function gx. So now let's use this function as an example. So first of all, we need to simplify this function if possible, right? Apparently, gx can be simplified to x minus 5 over 2x plus 5 by dividing both sides using a 2, right? If you cancel a 2 to both the numerator and denominator, you will get this simplified form, right? Okay, step 2, find the vertical asymptote by just setting the denominator equal to 0 and solve for x, right? So if we set 2x plus 5 be 0, you can solve that x is actually minus 5 over 2, right? So that means the vertical asymptote is just x equals minus 5 over 2. Okay, so we can draw the vertical asymptote first. Step 3, find the horizontal asymptote by analyzing end behavior. So according to the expression here, we can see that when x approaches positive infinity, gx must approaches 1 over 2, right? Why? Because when x is a very large number, the factors of these two numbers here can be ignored, right? So when x is very large, gx is actually approaches x over 2x, right? Which is actually 1 over 2. Understand? So same thing will happen when x approaches negative infinity. When x is a very large positive number, the minus 5 and plus 5 here can be ignored, right? So when x approaches negative infinity, gx also approaches 1 over 2, right? So that means the horizontal asymptote must be y equals 1 over 2, right? So now we can draw the horizontal asymptote on the graph. So now we have two asymptotes, right? Horizontal asymptote and vertical asymptote. Next step, we can calculate the x and y intercepts, which can then help determine the relative positions of one branch to the horizontal and vertical asymptote. So for example, we can just let x be 0 and then find that gx be minus 1. So the y-intercept is 0 minus 1, right? And then we can just let y be 0. So that means 0 equals 2x minus 10 over 4x plus 10, right? Solve for x, x is 5. So x-intercept is 5, 0, right? Okay, so x-intercept is 5, 0, which is here. And then y-intercept is 0 minus 1, which is here, right? So that means one branch must pass these 2 points, right? Okay, so you know that the two asymptotes are the dotted line, right? So this function must have a pattern like this, either this or this, right? And here you also know that this function passes through these 2 points. So this function cannot have a pattern with these 2 branches. This is not possible, right? So this function must have a pattern like this. In order to pass through these 2 points, right? Do you understand? The x-intercept and y-intercept can help you to decide one branch of the graph. The other branch is just to the opposite of this point here, right? Okay, so next step, as you can see here, one branch must be in the bottom right of the region divided by the 2 asymptotes, right? So we can just draw one branch here first and then use point symmetry to find the other branch, which is on the top left in this example, right? Okay, and now after you finish everything, you can just verify your result if possible using the property of this function. Okay, so now as you can see here, when x approaches negative infinity, this function here approaches positive 1/2, right? And when x approaches positive infinity, this function approaches 1/2 from the negative side, right? You can verify the result using the property of this function. This is a quicker way to sketch the graph of a function that has this form.
Alright, so now let's have a look at a practice. Sketch the graph of the function gx here. Alright, so first of all, we can find the domain, which is 2x plus 1 is not 0, right? This means x is not minus 1/2. So we know that the vertical asymptote must be x equals minus 1/2, right? Okay, and then we can find the horizontal asymptote. So note that gx equals minus 5x plus 3 over 2x plus 1, right? So when x approaches positive or negative infinity, you know that gx must approach minus 5/2, right? Because when x approaches positive or negative infinity, these two numbers here can be ignored. Gx must approach minus 5x over 2x, which can be simplified to minus 5/2. So we know that the horizontal asymptote is y equals minus 5 over 2, right? Okay, so we can just draw two asymptote first. Vertical asymptote here, minus 1 over 2. Horizontal asymptote is here. This is minus 5 over 2, right? Next, we can find the x-intercept and y-intercept. First of all, we can just let x be 0, and then gx is 3 over 1, which is 3, right? So the y-intercept is 0, 3. So 0, 3 is the y-intercept. Let's label this here. And we can let gx be 0. And we know that when gx is 0, x is 3 over 5. That means the x-intercept is 3 over 5, 0, right? Okay, x-intercept, let's label it here, 3 over 5. So that means this function must pass these 2 points, right? And in conjunction with the 2 asymptotes we have drawn, we know that this function should have a pattern like this. Right? This is one of the branches. The other branch must be here. Right? Okay, so this is a quicker way to draw the sketch of this function. Okay, and a sketch of the function should look like this. This is a nicer view of the sketch of the function. You can check it after the class. All right.
All right, let's have a look at another practice. Write an equation for the rational function shown on the following graph. All right, have you finished? Okay, so we can approach this question by analyzing the asymptotes first, right? Okay, note that the vertical asymptote is x equals 3, right? And this means this function probably has a form of this, right? Because x cannot be 3. Also note that the horizontal asymptote is y equals 2, right? So here we have a x2 in the numerator, right? And probably we'll add a factor a here. So in this way, as you can see here, when x approaches negative or positive infinity, the function will approach 2, right? Which is the horizontal asymptote. And also, x cannot be 3. That means the vertical asymptote is x equals 3. Next, we need to find the value of a, right? Also note that the function passes through this point. When x is 3 over 2, y is 0. This means 2 times 3 over 2 plus a over 3 over 2 minus 3 is 0, right? So this means 3 plus a is 0. And this gives us a is actually minus 3, right? So one possible form of this function is y equals 2x minus 3 over x minus 3. Do you understand? And you can verify your result by putting the y-intercept in, right? So note that the y-intercept is 0, 1, right? And if you put 0 in the right-hand side, you will get minus 1 over minus 1, which is 1, which is exactly the y-coordinate of the y-intercept. So that verifies our result here, right? Okay, any questions? No? All right, so basically this is all we have learned for today. Let's make a summary. Okay, so after this class, now you should be able to understand the definition of rational functions. And you should also be able to sketch or recognize the graph of the function of the form fx equals a over kx minus m plus c, and analyze their properties. And then sketch or recognize the graph of functions of the form fx is a ratio between two linear functions, and analyze their properties. Okay, I'll see you next time.